Welcome back to another video, and last time we talked about what are derivatives, and as you remember, it's the instantaneous rate of change of a function. Today we're talking about notation and all the different rules that can be applied to when evaluating for derivatives. Now, notation-wise, we have a few ways of representing derivatives. So, notation. Sometimes you're going to see all of these different notations coming around, and they all necessarily just mean the same thing. So you might see if f of x is your function, right? Then the derivative would just be f prime of x. We call this prime, right? And sometimes it could be dy over dx, which is just the derivative of y in respect to x. And that gets a little bit more complicated once you go on to like partial derivatives and everything else. But this is only for the first level. So this is for the first order derivative, right? But you could do the derivative twice. So if for whatever reason you need to do the derivative twice, you can still use a certain notation for it. In this case, since the first order of the derivative is just f prime of x, we can say that the second derivative is going to be f double prime of x. So over here we can write f double prime of x double prime. Okay, so that's how we're gonna write our notation here. Now we need to figure out like what kind of rules there are, right? And all that stuff. So our first rule for today is going to be the constant rule. So when we're dealing with derivatives, we have different, functions, right? So the constant rule basically just states that whenever we have the derivative of a, so in this case we're going to write d over dx, that also means derivative of, let's say, n, right? N in this case represents any number, any integer, any fraction, anything that has a constant value with it. So n equals a number slash constant, right? And that would ultimately just lead to 0. Because if you think about this in a graphical representation, where we have our graph of, let's say, x equals 4, right? This is our graph x equals 4. The whole point is that our slope is always going to be 0. So since the derivative represents the slope of a function, in this case, a constant can only have a 0 slope, right? Now, following on to our next rule, which is the sum rule, right? Sum or differences rule, we can combine those together. Sum or difference rule. In this case, right, we have, well, there's a certain way that we put it onto. So if we have two functions, right? Let's say we have functions of f of x and g of x, right? Those are two functions. Let's say that the primary function is just f of x plus g of x, right? And we're trying to find the derivative of that. So d over dx of f of x plus g of x, that's just going to be the same thing as the derivative of each function that we have there. So it's just be the derivative of f of x plus the derivative of g of x. Now you might ask me, what is a simpler way of writing this, right? let's use one of the notations that we used. So we could just say f prime of x plus g prime of x, right? Because those also means derivatives. Now, it's going to be the same case for our difference rule, right? So as if we just change the symbols here, d over dx of f of x minus g of x equals to the derivative of f of x minus the derivative of g of x, right? And we can write that as f prime of x minus g prime of x, right? So now those are the constant rule and the sum and difference rule. So we're gonna, of course, do some practice on later after we finish the last rule for this video, which is going to the power rule. The power rule is slightly more complicated, but it still allows us to evaluate for the derivative. So let's see, power rule. So as a power rule, it necessarily just means like exemplars of f of no, example equations would just be like x squared. It could also be like 5x to the cubed, right? So these are examples that we have basically for these types of problems. And the power rule states that the derivative d over dx of x, meaning like the variable that they use, they might use y, they might use z, it depends on the problem, and then x to the nth power. N in this case means any number. So by any number, it can only be a number. It cannot be like a variable or anything else, but it has to be a constant number. That is just going to equal to n times, well, the variable to the power of n minus 1. It applies to everything. So like if for whatever reason that they ask you what is the derivative of 5 to the x power, you cannot use this rule. It will not work on this rule because 5 to the x power is just going to be something different, right? We have a different operator for that. So by now knowing these rules, right, we can now derive for our derivative rule. But before, we can arrive for our variable rule. But before we do that, we should at least prove saying that, the rule for this by the difference quotient, right? So on the last video, we saw problems about finding the derivative of x squared, and it came out to be 2x, right? If we apply the same rule to it, we will find that it's going to be equal to 2x, right? If the function was x squared. So the main reason how we found this out by having the proof, right? I'm going to try doing the proof on the spot right here. We have this rule, right? And x to the n power is basically just the variable that we have, right? So let's say f of x is equal to x to nth power, right? Now we can use the difference quotient. So the limit as h approaching 0 of f of x plus h minus f of x over h equals the limit as h approaches 0 of, let's say, it's going to be x plus h to the nth power minus minus x to nth power over h. So now if we really wanted to expand this out, we can use like the binomial theorem, and especially whenever it becomes like x plus h to the cubed or x plus h to the fifth power, we're gonna have to use the binomial theorem. But in this case, we're gonna make it a lot easier because for the first term that we have, right, we have it's always gonna be minus x to nth power. And the first term that we get from this function of x plus h to the nth power, the first term is going to be x to the nth power. So we can cancel those out real quickly, right? So now, how we're going to evaluate this is, think about it as in concepts of like applications, right? So if it was like x plus h to the second power, that's just going to be x squared plus 2xh plus h squared. Now we see like a common thing around here where we have all of this, right? So that common thing, like let's say, I'm gonna write this down on the top here. Let's say if it was let's say if it was x plus h to the second power, that is just equal to x squared plus 2xh plus h squared. We see a common thing here because our exponent is, of course, 2, right? But then at the same time, the exponent for our first term with the x is also 2. Our coefficient for our second term is also 2. And also for our last term, the exponent is also 2, right? So now that's a pattern that we have here. The 2 is basically just the end number here. So if we write x plus h to the n power, it's just going to be equal to x to the n power plus nxh plus h to the n power, right? If we write it like simply like that. And of course, once we get to like a higher order, then we have to change this up because the nxh in the middle, this term, it will not always work because let's say you have like x, let's say you have it to the third power, right? Then it won't work that well enough. So x plus h to the third power is just equal to x cubed, right? Plus, let's see, so it'll be it would be, let's see, so using Pascal's triangle, right? 1, 1, 2, 1, right? So, and then 1, 3, 3, 1. So it'll be 1 in the front, right? 3 x squared h plus 3 xh squared plus h cubed, right? So by using Pascal's triangle, we can figure that out. That's the binomial theorem, which we haven't discussed yet, but it's a complicated process, but it's good to know for reference. So now, since we have that all cleared out, right, we're looking at the x's, right? So the middle terms, they have x squared, and of course, it's going to be x to the n minus 1. So you can clearly see this difference here, over here. So on the top, you have 2xh. On the bottom, you have 3x squared h, right? But for the first equation that we use for the squaring, our n number equals 2. For the next one that we just did, the n number is equal to 3, right? So since we're going to highlight all of the n numbers, right? We got 3 here, we got 3 here, we got 3 here, and then we got 3 up here, of course. But we still have the 2, right? Which is something that we didn't look over on the first one, since it's like an invisible exponent. We just know that's there. So this 2, we can represent it as n minus 1, right? So by using all of this to figure this out, right, we can of course figure it out. Okay, so it's going to take it in the form as x to the nth power, right, plus n times x to n minus 1 and of course of h as well, right? Plus h to the nth power minus x to the nth power over h. And also don't forget the limit here. Alright, so now, since we just figured out this whole entire process of like how we're gonna get this to the equation that we have so far, we can start crossing out whatever we have that are like terms, right? So x to n minus x to n, that's gone, right? H to the n and over h, that'll just be h to the n minus 1, right? Because you're deleting an h from the exponent. And then, of course, on the n times x to the n minus 1 power times that h, of course, the h will also cancel out here. So at the end, you're going to have the limit as h approaching 0 of n to the x n minus 1. I should write down, let's do this. N to the, well, n times x to the n minus 1 power plus h to the n minus 1. And if we're going to substitute in the 0 for everything, this will just lead us to nx to n minus 1 power. You see how this is basically just the same thing as what we stated up here with the power rule, right? Now, it's something that we're going to apply to, right? We have these proofs and everything, right? And everything's going to make sense at one point, okay? So now, let's get a little bit underneath and try to reveal something from this power rule, right? So what if it was just x? Let's say the function was just x, right? The slope is 1. So in theory, the derivative of any variable by itself with no exponent is just equal to 1, right? You can still have a coefficient. Yeah, you can still have that, right? But just not like an exponent or anything. That also brings me to say that let's say you have a coefficient in your function, right? Like this example up here where I have the 5x the cubed, right? That 5 can be put outside of the derivative just because it's a coefficient, right? So no matter what, it's going to be multiplied by that, okay? So let's try some examples and understand all of this real quick. So we have the function f of x is equal to x squared plus 5x cubed, right? That looks simple enough. Now, what is the derivative of this? So the derivative of this, without using the difference quotient and only using the rules that we applied, x to the second power, right? This is just going to be the same thing as d over dx of x squared plus d over dx of 5x cubed. Now, this is mainly because of our sum rule, stating that whenever we have a sum in the function, we can split those apart and get the derivative of each term that we have, right? Now, we can evaluate this, right? So now, the derivative of x squared, we know, is 2x based off of the power rule, right? And then plus, now this is where things get a little bit complicated because we have a coefficient here, right? For the 5x cubed, we have a coefficient of 5. So we're going to place that 5 outside of the derivative. So that'd be 5 times the derivative of x cubed, right? So in this case, we applied the power rule and the coefficient rule. Alright, so since we understand all of that, right? Now we can get to evaluating the last term. the last term, the derivative, right? We have the n times the x to the n minus 1 power. N in this case is 3, so we're gonna times this by 3. Our variable is x, right? And then n minus 1 is just 2, so we put 2 as the exponent. And of course, if we simplify it, it'll lead us to 2x plus 15x squared. That is our derivative of x squared plus 5x cubed, right? So I'm gonna write here, we use the power rule. And that's it. That's how easy it is. So now we're gonna try some problems on your own, and we're gonna check back in and see how well we can get those problems in, right? So let's say f of x is equal to 5x to the 4th power minus 3x plus 2. Find f prime of x. Now, take a moment and pause the video here and solve this out by your own. Alright, so hopefully you just pause the video and looked at the problem on your own and try to figure it out. Now, we're going to get to solving it, right? So now, we have 3 terms here, right? We have 5x to the 4th power, we got negative 3x, and then we got plus 2. So, since we can use the sum and difference rule, let's use that first, right? So f prime of x is just going to be equal to d over dx of 5x to the 4th minus d over dx of 3x plus 2 plus d over dx of 2. d over dx of 2. Alright, so now let's start evaluating for this limit, right? So f prime of x equals to the derivative of 5x to the 4th power is just going to be 20x to the 3rd power because of the power rule. And then minus the derivative of 3x is just going to be 3 because x is the variable, and since it's by itself with no exponent larger than 1, it's going to be, of course, equal to 1. So we have minus 3. And of course, the derivative of any constant is just 0. So our answer here is just 20x cubed minus 3. That wasn't that bad, right? Let's say for whatever reason you want to find the second order derivative. So now in that case, you would just do the derivative twice, basically. So you would find the first derivative, and then you would find the next derivative. It's just like series in algebra 2 and trigonometry, just that it works the same way there. So, you know, if you want to find the third derivative, which they probably won't tell you to do that, but in some cases they might do, and you just find the first derivative, and then you find the second derivative, and then you find the third derivative to figure out your answer. So now, during our previous video, we mainly talked about the basics of derivative rules, like the constant rule, the sum and difference rule, and just the power rule just in general. And also we tried to prove some of those. But this time, we're going to be talking about more of the more complex functions, as I used to call it. For example, like e to the x power, or any number to the x power, right? So let's start with exponential functions here. Exponential functions. Now, some examples of these functions would be like, let's see, e to the x power, or 5 to the x power, or 5 times 6 to the x power, right? those are just a few examples of what we call exponential functions. It's because on the graph, they're moving up exponentially, hence why the name of exponential function. Now, you might ask, oh, what is the derivative of e to the x, right? So now, the derivative of e to the x is just e to the x. And then now, since you guys know what the derivative of e to the x, do not get it mixed up with any other value that we have here. So the derivative of 5 to the x would be different from e to the x. So now, let's state that we have a constant inside, like as the main factor, right? So it would be like n to the x power, right? N equals any number. Now, the derivative of n to the x will just be n to the x, but you have to times it by ln of n. So it's not too bad, right? So, as a few examples, if we had d over dx, the derivative of 5 to the x, right? That's just going to be equal to 5 to the x times ln of 5, right? Because you're maintaining the original function, but then you're also adding onto the ln of whatever number you have. So the 5 here in this case. Alright, so next, let's try a example on your own by using these rules that we have here. Let's say you have to find the derivative of 5 to the e of x minus 3 to the x power. Take a moment here and pause the video and see if you can figure this out. Hopefully you just pause the video and try to figure this out. So now let's try to use the rules here. So since we know that for our first term is 5 to the e of x, and then our second term is 3 to the x, we can use this difference rule, right? So we're just going to take the derivative of each of the individual terms. Minus d over dx of 3 to the x power. So now we're taking a look at this, right? And we see that 5 in the first term is just a coefficient. So we can bring that outside in this case, right? So now the derivative of e to the x is just e to the x. So our first term stays the same as 5 e to the x. Now our second term here, the second term that we have is a little bit different, right? It has a number, but then x is as exponent, right? So now we keep it the same, but then we multiply it to ln of the base. So ln of 3. And that is our answer. right? So as a recap, exponential functions, they you can solve for the derivative of them just by these two different rules here. Remember that e to the x is not the same as any number to the x power. So you have to have a separate rule for that. Now our next topic here is logarithmic functions. So let's write that down. Logarithmic functions. So now a few examples of these, right, would just be ln of x or log base 5 of x, right? Now, since these are examples, right, we can use this similar structure here. So the derivative of ln of x is just equal to 1 over x, right? Now, the derivative of, let's say, log base a of x, right, equals 1 over x ln of a, right? So make sure that, you guys don't forget that it's different with these two functions, even though they might look the same, right? So as an example that we might have is like, oh, find the derivative of ln of x, well, 5 times ln of x, right? Now 5 is the coefficient here, so we place it on the outside, so that would just be 5 times 1 over x. That's simple. Now let's say it was find the derivative of log 5 of x, right? Then that'll just be equal to 1 over x. Remember, x stays the same, but then you take the ln of the base, which is ln of 5. Now take a look at this example for yourself and see if you can solve it. So find the derivative of 5 ln. Actually, let's make it 6 ln of x plus log 6 of x. Try solving this out. Hopefully you just pause the video there and try to solve it for yourself. Now let's get right into it. So we can see that they're separated by a addition symbol, so we can use the addition, the sum rule, right? So we have two terms here, right? So we're gonna take the derivative of each of these integer terms. So the derivative of 6 ln x plus the derivative of log 6x, right? Alright, so now, since we know that 6 is a coefficient, we can always bring it onto the outside because of the coefficient rule, right? And now, this would equal to, just by taking the individual terms, 6 over x plus the 1 over x ln of 6. And that is our answer. Alright, so this is where it gets a little bit confusing because now we're entering trigonometric functions, including its inverse, right? Now we have a total of 6 trig functions that we usually use, and let's write this down. Trigonometric functions, right? So now we have 6 of them. D over dx of sine of x, right, equals what? D over dx of cosine x. D over dx of tangent x. We have the derivative of cotangent x. And then the last two ones are just secant x. And last one is cosecant x. Alright, so now, since we have all of these 6 different trig functions, the last two are a little bit more complicating. Well, the last 3 is more complicating. But the first 3 is served as like a basis because the first 3 appears the most common, I would say, out of like all the AP tests and stuff like that. But you still gotta memorize all of them just to be prepared for it. Alright, so the derivative of sine x is just cosine x. The derivative of cosine x is just negative sine x. Now, you see a little pattern there, right? Where it's just the reverse, the opposite signs, right? Now, the derivative of tangent x is secant squared x. And the derivative of cotangent x is just negative cosecant squared x. Now, you also see this pattern here where the co of the original trig function is a negative, right? So now, if the derivative of secant x is just secant x times tangent x. But on this side, where we have cosecant x, it's going to be negative cosecant x times cotangent x. Right, so those are our different functions that we have here. So as an example to show, right, as an example, we can use sine x plus cosine x, right? Find the derivative of that. Now, since they're both separate terms, we can just solve it right off the bat. So the derivative of sine x is cosine x, and the derivative of cosine x is just negative sine x, so just minus sine x. And that's your answer right there. Alright, let's give you another practice problem here. So the derivative of, let's see, tangent x plus a secant x. Try solving this. Take a moment for yourself. Or hopefully you just pause the video and try to figure it out yourself. Since they're both separate terms, we can just take the derivative of each. And that will lead us to the derivative of tangent x is just secant squared x. And then the derivative of secant x is just secant x times tangent x. And that is your answer right there. Now, you might ask, what if it was inverse trig functions, right? Because those act a little bit differently here. So inverse trig functions. Now, of course, we're gonna have the same trig function that we just had, but just the inverse of them. So now there's two ways of writing the inverse of these functions. One's by using the notation where there's the -1 as an exponent, but then the other way is just using arc. It's like arc sine, arc cosine, arc tangent, right? So those are the two ways. I'm gonna write both of them just so that we're all clear on them. So for the first one, let's do the derivative of arc sine x or sine -1 x. And that's just equal to 1 over the square root of 1 minus x squared. Alright? Now, for our second one, we're going to do the inverse of cosine x. So the derivative of arc cosine x or cosine -1 of x. Now, as we've seen in the previous problem where it has the negative, it also applies here. So this will just equal to -1 over the square root of 1 minus x squared. Now, third, we're going to have tangent x. So arctan of x or inverse tangent of x equals to 1 over 1 plus x squared. Then we have arc cotangent x, or just inverse cotangent x here. And that, you can tell it's equal to -1 over 1 plus x squared. And for the last two, which we probably never gonna use ever, it's just arc secant x or secant to -1 of x, right? And that's just equal to 1 over, this one's a little bit more complicated here, the absolute value of x times the square root of x squared minus 1. And of course, last but not least, of arc cosecant x or cosecant -1 of x equals 1, well, the negative of 1 over absolute value of x times the square root of x squared minus 1. There you go. So now these are different trig functions for inverse, and we barely use them, but I think once in a while you're gonna see one approach you. So it's good to keep it in the back of your mind. So now, next video we're going to talk about more of the product rule, quotient rule, and chain rule, just so that we can finish off derivatives. And once you guys understand all of these rules, you guys can put them together, do whatever you need to solve the derivative that is like really complex. So now these are different rules that are a little bit more complicated when dealing with the derivatives, because some derivatives you can't actually figure out just by using the sum and difference rule here. So as we get along with it, we will do a lot of practice, and hopefully by the time we're done with the video, you should know a lot about it. So our first rule is the product rule. Now the product rule states that if f and g of x are both functions, then the derivative of f of x times g of x is just equal to f prime of x times g of x plus f of x times g prime of x. Right? So now it's going to be like the first part of the equation is like the opposite of the second kind of the equation. So you have the derivative and then non-derivative. And then you add the non-derivative and then the derivative. So another way that we can like memorize this is by what some people use, fig GIF. Fig plus GIF, right? In this, it's saying that f prime times the g, and then the g prime times the f, right? So it's the same concept here. Now let's do an example together. So an example could be find the derivative of x plus 3 times x squared. Now, you might say, hey, why don't we just, like solve this out and then we can use a power rule, right? But the whole point of the product rule is that once you get into like trig functions, it's going to be a lot harder to figure out, and it's another simpler way of doing it so that you don't have to take that much time. So now we know that f of x, let's do this. We know that f of x is equal to x plus 3 because that's the first function. And then f prime of x is just equal to 1 since x is its own, x is a variable and the derivative of any variable is just 1. And then we have g of x is equal to x squared, while g prime of x is just equal to 2x. Now let's put that all together in this form. F prime x, g of x plus f of x times g prime of x, right? So f prime of x is just equal to 1, so we can cross that out, equals to 1. G of x equals to x squared, so we do x squared plus f of x, which is x plus 3, and then g of x, well, g prime of x is just 2x. In rare cases do they tell you to expand it, but in this case we will expand it because it's a lot easier. So that'll be x squared plus, let's see, 2x squared plus 6x. And that'll lead us to 3x squared plus 6x. And that is our answer here. Now, we can of course check this by just, factoring things out here. So the derivative of x plus 3 times x squared is just the same thing as the derivative of x cubed plus 3x squared. And by using the power rule here, the derivative of x cubed is just 3x squared, right? And then plus the derivative of 3x squared, which is just 6x. And we still get the same answer, right? Alright, so now try this example on your own, where you're asked to find the derivative of, let's see, what can I give you? The derivative of x squared times sine of x. Take a moment and pause the video here and try solving this out. Alright, hopefully you just took a moment and solved it out. We can tell that f of x, our first function, is just equal to x squared, and g of x is equal to sine x, right? Now, f prime of x is equal to 2x, and then g prime of x is equal to cosine x. Now, if we apply the rule that we had, was f prime x times g of x plus g prime x times f of x. Now, remember, using the commutative property, you can switch around the terms here. So now, just for uniformity, I'm just going to write it the other way around. F of x times g prime of x. And now we can start plugging in the stuff. So f prime of x in this case is just 2x. 2x times the g of x, which was sine x, right? Plus f prime of x, f of x is x squared, times g prime of x, which is cosine x, right? Cosine x. And our simplified equation is just 2x sine of x plus x squared cosine x. Now that is our answer here. So it wasn't that bad, right? Now, a common mistake that people usually do when entering these problems is that they multiply the derivatives around. But in this case, do not multiply the derivatives around, because once you do that, then there serves no purpose of the product rule. And in this case, the x squared times sine of x, you can't really multiply that together before you evaluate the whole thing. So in some cases, you have to keep it like that. Now, continuing on to our next subtopic, it's the quotient rule. Now, the quotient rule is a lot similar to the product rule, just that instead of a plus, it's a minus, and then it's over the last function squared, right? So let's say that f of x and g of x are functions. Then the derivative of f of x over g of x is just equal to f prime of x times g of x minus f of x times g prime of x over g of x squared at the end. So now you might tell me, this is a little bit complicated, right? But you can tell that the beginning, the numerator, is a lot similar to the product rule, and then the only thing that changed was just the symbol, and also just that you put it over the original function, the original denominator squared, right? So using this rule, let's see if we can try to find this example. Let's do an example, right? So we're here trying to find the derivative of x cubed over x plus 1 here. Plus 1. Now, our upper function, our numerator, is just x cubed, right? And our g of x is just x plus 1. Now f prime of x is just 3x squared, and g prime of x is just 1, right? So now let's put it into the equation that we have here. So of course f prime of x times g of x minus f of x times g prime of x over g of x squared, right? So now once we put it inside the equation here, f prime of x is 3x squared, right? 3x squared times the g of x, which is x plus 1, minus f of x is just x cubed, times the g of x is just 1, so we can keep it the same here. And that will be all over g of x, which is x plus 1, squared. Now, they usually don't tell you to simplify this, right? Because it sometimes becomes like a hassle trying to simplify it, right? So we're just gonna keep it like this. This is our answer. And yeah. So now let's try doing a practice problem by yourselves. So let's try it with this. So find the derivative of sine x over x. Try this on your own and pause the video here to figure it out. Alright, hopefully you just pause the video and try to figure this one out. So now, let's try to solve it. F of x, the numerator, is just sine of x. F prime of x, we all know it's just cosine x. G of x is just equal to x. And then g prime of x is just equal to 1, right? So now, let's put this in the equation. So the equation is f prime of x times g of x minus g prime of x times f of x, right, over g of x squared. So now this would equal to f prime of x is just cosine x times the g of x is just x minus g prime of x is just 1, so f of x is sine of x, stays by itself, all over x squared. And that is our answer. So once you get into like a habit of these things, then it's going to be something that is going to click in your head very soon. A common mistake that people make is that they set it to addition instead of what's supposed to be like a subtraction. And also, you only square the denominator. You do not square anything else in this equation. Alright, so for our last rule for derivatives, it's called the chain rule. Now, the chain rule gets a little bit complicated because you're dealing with inside functions and outside functions. So you have to really break it down and see what you're trying to have here, right? So now, chain rule. We call it chain rule because at the end, it usually just forms a chain of like the terms and stuff. So that's why we call it that. And if f of x is the outer function, right? And g of x is the inner function. So now, the derivative of f of g of x, that's what it's gonna look like. It's just equal to f prime g of x the g of x stays the same, times the derivative of g of x, right? So that's what the whole entire point is. It's gonna get a little bit complicated for the first few times that you're trying to do the chain rule problems. For me, it was a little bit complicated for me as well. I didn't get it the first time, but as you practice more and more, then you're gonna understand it more. So now, since we have this, right, let's do an example here. Our example is find the derivative of 3x plus 2 to the 4th power. Alright, so in this case, we can tell that our outer function, which is f of x in this case, right? F of x is just equal to the parentheses to the 4th power, right? And now our g of x here is just equal to 3x plus 2, because that's the inside, right? There we go. That's the inside of the part. And then you have the g of x here. I mean, the f of x. We have exponent of 4, and over here you have exponent of 4 as well, right? So now we're going to try solving this here. So since we're using the base equation of f prime of g of x times g prime of x, right? That's just going to be equal to, we know that f prime, since it's to the 4th, right? We're going to make it seem like it's x to the 4th, just like as a placeholder, right? For the inner function. So since x to the 4, the derivative of x to the 4 is just 4x to the cubed, right? So 4 times the inner function here, 3x plus 2 to the cubed, times, now g of x is just 3x plus 2, but the derivative of g of x plus 2 is just 3. And that simplifies to 12 times 3x plus 2 to the 3rd power. Now you see how we took this spot here, the inner function spot, and just replaced it with g of x, right? So technically we can say that f prime of x is just equal to 4 to the something to the 3rd power, right? Because we're using that same power rule here, and then of course g of x is just equal to 3, right? Alright, so let's try an example on your own here and see how it works out. So the example that I will give you is of course with trig functions, and then we'll try another one. Find the derivative of sine of 5x. Pause the video here and try to solve this out. Alright, hopefully you just pause the video and try to solve this out. Our f of x, well, our f is just equal to sine of blank, right? And then our g of x in this case, the inner function, right, is just equal to 5x. Alright, so now, since we have to find the derivative of f prime of x, right? Now, the derivative of sine is just cosine, right? So just cosine in the parentheses. And of course, g prime of x is just equal to 5, right? The derivative of 5x, right? And the base equation says that f prime of g of x times g prime of x. So now that's just going to be equal to the cosine of 5x times g of x is just 5. And we can reorder these terms to make it look better by just moving 5 to the front here. So it will equal to 5 times cosine of 5x. There you go. That is the answer to this problem here. Now let's try one last example, but this one we're going to incorporate some exponential functions here. So find the derivative of e to the 2x squared. Take a moment and pause the video to try to find this out. Alright, hopefully you just solve this equation out, and let's try to solve it now. So our outer function is just e to the whatever power that we have here. Our inner function in this case is just the exponent, so 2x squared, right? Now, f prime of x is just equal to e of whatever exponent we have, because the derivative of e to the x is just e to the x, right? And of course, g prime of x is just equal to 4x, right? So now, let's try to solve this out here. Using the base equation of f prime of g of x times g prime of x. F prime is just e to the whatever power there is, so we can write that first. E to, well, g of x, right? G of x is 2x squared times the derivative of g of x. So that's going to be 4x. And once we reorder these terms, it's going to be equal to 4x times e to the 2x squared. There you go. See, it wasn't that hard. So now, make sure that you practice a little bit more, right? And of course, once you complete everything, right? Once you do everything, make sure that you double check it. And in the future, once you get to integrals, you're gonna have to really double check your work with all of these things. And once you get a good basis on derivatives, everything else is gonna be a lot easier than it should be. So make sure that you keep on practicing, and make sure you guys practice the product rule, quotient rule, and chain rule, because those are the three, one of, I would say, the most complicated rules out of everything. So make sure you practice those, and I will see you guys in the next video.